So welcome back for lecture 2, Parallel Programming with MPI in our HPC course. In the first part of this lecture, we understood a little bit the overall idea of MPI. We connected it a little bit with the idea of having a simple C program that we did in practical lecture 1.1. And now wanted to extend that basically to a valid MPI program. But before we go in that way, what we will do in this particular part, we also learned there are certain terminologies in MPI that are existing, things like ranks, right? So unique ranks for every processor involved. There are point-to-point communication, let's say functions available, the send and receive. And that is an important principle. Think about the ball analogy, right? We have here just now the handball very as a hot topic. So that means if one player is throwing it, the other should be ready to receive it. Otherwise, the message, so to speak, the ball will go to somewhere and doesn't help us. In the same way, we have to program code that one rank is sending and the other one is receiving. Think about a ping, right? And then when you want to do a pong, let's say backwards, then of course the other one should be also ready to receive while you do the pong now. So we will talk about this ping pong as a fun application at the end. But we will also try to now establish a little bit how we can come from the simple C program we started with to really a very initial MPI program that we then again can extend in further lecture. Like 2.1, I will show you many demonstrations and examples, but also then, of course, in lecture 3, lecture 4, when we have much more advanced examples of communicators. So communicators is another loaded term in MPI. Mostly because you have, different various about it. You have seen the Cartesian one, where we, for instance, have a water of some kind, and we maybe want to have a 4x4 grid for fish simulation, for ship movement. Or we have the other one that you have seen maybe just based on functionality. We had this group MPI Com World, the communicator, where all the processors are in. And then we create subgroups from that, where one is just calculating the waves of the ocean, while the other one is calculating the ship on the ocean, right? So another idea of how to use parallel computing. But again, this would be already, let's say, advanced applications. Hence, we will come to this now in a couple of lectures. Let us start now by what you already know from the last practical lecture. And this is really thinking about first, what do we need? Obviously, when we have MPI, the sort of 0 step before you start everything else with programming, you have to think about, okay, in what I want to program MPI. Hence, you need a specific implementation. In our case, we use the OpenMP MPI standard. This could be also something which is a bit depending on the systems you have. For instance, in the Jülich Supercomputing Center, the deep system, we have the Parastation MPI as well. So it depends also which of the systems are offering which MPI implementations. Usually you don't want to really, create and compile and do and prepare these environments. You want to do is just module load, right? What you learned the last time in 1.1. But they're different implementations. They have their unique selling propositions here and there. So for us in the course, it doesn't matter so much. These scales, don't worry about this. Hence, we will stick mostly to the OpenMPI. Now from the stepwise work, when you say, okay, now I want to do this, you of course pick a system, right? So that's your first step. I want to do an MPI application somewhere on Elia. Hence, before you go there, we have our old approach of using the SSH key. By now, you're probably tired when I talk about this public and private key. You have heard this many times, never share the private key, use a public key, give them away. And when you want to have the SSH, present your private key once, but always keep it on your laptops or on your desktop. Or you give away as a public key. And if you give this to the administrators, this will be part of assignment 1. That's why I'm saying it's a very practical oriented lecture. And on Monday, I will demonstrate it with you in practical lecture 2.1 again. But the login is, of course, number 1, right? So that's what you know already. So no surprise there. We also have our old Hello World C program. So that's also what we had the last time. No surprise there. You should also start then creating maybe HPC course folder once you get the account next week on these systems, will be also part of the assignment, don't worry. You make a directory, and then you have seen in my practical lecture 1.1, we have a typical text file we just edit, and then have this couple of statements, which is, very trivial C code. but already captures the essence of what we want to do today in parallel. We want to have 4 times hello world printed out by 4 different processes, right? They don't solve a problem in a cooperative way, which usually should do, but this would be then something I present in 2.1 and in 3 and 4 in further lectures. Today, it's just to understand how scheduling and how the MPI environment helps us to do something in parallel. And this should be the hello world. Now, we can still start from this program. It's a very basic C program. Everybody understands it. It's a main function. It returns 0 if there's a good outcome, and we have a printf statement giving hello world out. Similar things you have done in Java in a way to have this printout. Now, the printout is also for us important. We don't want to have this on the screen anymore, right? We want to have this in a file. It will be also part of scheduling. So let's extend this now in the next step to have basically an MPI program and to think really in parallel. This is a bit a bigger topic relating to something we call domain decomposition. So how you want to, again, parallelize your domain. And we will talk about it extensively in lecture 3. Right now, for us, we want to do it as a very, let's say, simple idea, simple process, multiple data. So in the way, we want to have the same program, the same process from the application perspective on different cores executed, right? So in this sense, a so-called SPMD application, the same source code in other ways. You take the same source code 4 times, it just works on different data. Now, this is also an interesting effect. So when you have the same source code, you need to understand there must be something inside that makes it different for all the different cores. Hence, there comes something in like ranks, because every process, every core will know its unique rank according to all of these processes. It's not obvious to you. We'll see how that materializes. But that is basically the first part where you have to start thinking in parallel how you want to parallelize it. Then, of course, what data is needed. Now, in the hello world, we maybe want to add something, right? We say we have now 4 times hello world. I want to know where it's coming from. Is it core 0, 1, 2, or 3? So let's extend that of saying I am core 0 out of 4, right? Our group for 4. That already gives me, let's say, some application logic part where I know I am a unique rank. So, and I can use this, obviously, if you think a bit further, for if statements. If I'm rank 0, then I do this. If I'm rank 1, I do something else. And this will be a very important program district. Thank you. Which we also will use later, and I will show you step by step, particularly in the ping pong application, because you have to know, are you in the ping time or in the pong time, right? So a bit fun along the way. Hence, this is the first thing to really start thinking in parallel. You have to leave a little bit what you learned in this Java courses and the software engineering courses with big classes everywhere. Here we're thinking rather how we use different processes in parallel to solve a problem. And we start by adding these 2 important variables, rank and size, which basically almost all MPI applications, if not all, have both. And this is basically the variable where we store the unique rank in. In other words, what process I am. Process 0, 1, 2, 3, it always starts with 0, computer science. And then size means how many others are basically in my domain of application. This also will give us an important part called scalability of the application. I can execute it with 4 hello worlds, 8 hello worlds, 12 hello worlds, and don't change the source code, just the job script. And I will demonstrate it to you basically on Monday. Hence, also a bit different if you think. And as I said, also we want to add something here. Here we just use the common idea in C to basically have variables printed out. That's why this placeholder, you would say, is here. And basically, you see during the runtime, there will be rank here and size, depending on the real application in place. And then the rest is still a valid C program. All we did was extending a little bit to arguments and the command line parameters that we want to work with in future applications. Hence, very easy to add, right? It's still a typical C program. There's nothing bad in this. We still need to add a couple of things now to make it very MPI specific. This was just typical integer variables, so you could use that for something else, but now we want to have the MPI functionality with it. And this means, firstly, we want to have our MPI header. Hence, the MPI implementation will be now linked when you compile it and so on. And there are two important parts which are always basically in every MPI application as well, the MPI init and the MPI finalize. So between those aspects, we have the real parallel code. That's where we can program in parallel because the MPI environment is established. I explain this also later a little bit. And then we still have to figure out how rank and size are actually filled from this environment. Hence, we need another function as part of this, which of course then fills essentially this type of information. This is a bit more elaborate because, as I was saying, this is depending on a certain communicator, right? So let's assume we have a job here. You see that from 0 to 9, so 10 processors. This is MPI world because every processor that will be part of this applications, when I have number of tasks specified in my scheduler and say I want to have 10, everyone gets a unique rank inside this MPI world communicator. So this would be one that is always existing. This communicator is, so to speak, the de facto standard there. You can create your own subgroups, your own communicators. That's why you can have different ranks in different communicators, right? You see a little bit here where this is alluding to. Basically, you would say if you take the processors from 1 to 9, you take them into groups, and they would have their rank in this MPI world different than your new created communicator, where you have both basically from 0 to 4. Hence, in a way, you can have different ranks, but this is really for later. Take away the message that in the beginning of the course, we really need MPI world, where it's a world of all the different processes we talk about in parallel. And there are these two important things. Firstly, the com size. And this is nicely now that MPI gives me this back. In other words, basically you get this through the job script, this information through the MPI environment that 10 cores are used. And then it is automatically filled with 10, right? So we know, okay, we specified in the job description in the job scheduling script, submit hello, basically the number 10. Could be 8, could be 20, could be 15, right? And you see it's independent from the size in the application itself. I still can compile that and it would always work. I don't have to recompile if I want to work it with 4, with 8, with 12 processors, because our job script will basically give the hint through the MPI environment. And this will lead later to really scalable applications where you maybe program initially for 256 cores, but essentially over time you go to 1024, you basically extend, but your source code remains the same. Then you do performance analysis, you will understand, okay, actually my problem is scalable, or you will see a degradation of performance, something we will establish in lecture 3, where then load imbalance and other problems will take place. So not every application like our beautiful hello world is basically infinite scalable, right? Here is nothing big to do, so we can have 100,000 cores and everybody would say hello world. Not very productive, but it shows a bit the idea of the scalability. The rank is of unique importance because it's unique, right? No one else has in this world of communicator this rank. Hence, this is beautiful for us because we will later see we can use it really as application logic. And again, here, the application should be run in a way that you don't really program it for a specific number of processors. I hope that's so far clear. Any question on this fundamental concepts? It's obvious, right? So it's not so much rocket science, but in fact enables us now for running it. Again, the steps are very, let's say, straightforward, as you know from the C program. We are logging into Elia. That's what we have done in one of the earlier steps, just to check we're on the login node. Okay, that's not a problem. Hence, I don't want to basically run it here, but what I can do is compile it here. When I have the MPI header in and MPI statements, I need an MPI application, or basically the library for it. Hence, I'll use a module load MPI / OpenMPI 4.412. And now I have basically access to the OpenMPI implementation and use the compiler of it with MPI-CC to create now our first real MPI program. Right now, the first time we really use parallel programming. Before, it was just C. We could just use a normal C compiler and so on. But the idea is to give you a smooth transition from the typical C program to an MPI program. The MPI program has the only disadvantage, it is in isolation to each other, right? There are no send receive messages. As you know, everybody has data on its own and says hello world, and will figure out, okay, I am so much rank out of this number of processes. So you would say MPI lives from message exchanges, right? That's why I want to use it. So it's in a way a very small application, but it carries already some essence of how to work in parallel. And we're going to extend it again further to have this application logic started. Hence, the module environment is of particular importance. I talked in the last lecture already about modular whale. We will do the same exercise in practical lecture 2.1 to do more elaborate things. Compilers, MPI is one part, parallel file system, parallel file formats with the HDF or the netcdf, as for instance, another module when you want to store data in parallel using concurrent access to files. So these are all examples where you need specific libraries and you have to module load them in order to use them in your application. Hence, the module environment is always sort of your first thing to check what's available on the system. Can we use the system? Is OpenFoam there? We will see that later with the CFD special, where we look, is there ANSYS, maybe another certain package installed, and so on. So that's important when you basically work with the systems, but we had this also already now a couple of times presented. So when I load the right modules, right, like for instance, now we had our beautiful MPI, OpenMPI. That's the first thing to do, to use this compiler. Then I have this hello executable. If you remember, this was the one with the X's here, right? So it can be really executed. It has been compiled without errors. I basically have not only a full C program now, I have also a full and valid MPI program now. Admittedly, not very sophisticated, but still works. And I have this compiled with its different steps. This -O is a bit optional. I would recommend you to use that. It defines a little bit how the executable is called, right? Otherwise, it would be, let's say, very random names. And here you basically can steer it a little bit. It will be important for later lectures when we have different examples to get a bit more clarity in all your source code. Hence, here's basically nothing new what we have done before in lecture 1.1. The only difference maybe is now that we have this MPI statements in this hello C program, but still our executable is the same. Hence, we also want to submit it now basically the same way, right? So we have to not do now the point of using the login node to execute it. We learned that's the wrong way. So let's use a scheduler as the next step. When doing the scheduler and this next step, we, however, want to realize something which was new, right? So hence the changes actually in the C program are often not that crucial, but the changes in the job script are now. Because now I want to achieve that I don't have one hello world and submit it somewhere. I want to basically have it 4 times executed with 4 cores. Hence there is an environment called MPI run that takes care that your executable hello that we created in the Lego node is basically transported to these different processors. That one thing. And of course, this MPI environment is then creating 4 processes. And the beauty of this MPI is it creates them in a way that we have rank and size basically available in this information. So hence what we want to get out is that each of these is a very same source code, right? It's just one executable, once compiled. I just ship it out to 4 cores. The result, however, is not the same. I get my statement, hello world, I am 3 out of 4, I am 0 out of 4, I am 2 out of 4, basically coming from the environment. And this enables us to think really that the submit script, when I influence MPI run and say, hey, I want to make it on 8, just do it on 8, you have no changes to the source code, right? It will distribute it on 8, and then you basically, the only trouble you have maybe that, you know, basically the kind of, how to say it, the order of the outcome will be made messy because essentially all write at the same time to a file. So it means you cannot expect that this will be deterministic, right? There will be 2 out of 8, 7 out of 8, but it will be not beautiful that I am, you know, 0, 1, 2, 3. That is something to do with, let's say, race conditions on the output file that one process wants to write, but the other one is already in. The ones that first basically writes is a winner. That's why you will see if you basically do that very often, like you do in your assignment, that the order will change. But in the end, that's not very relevant for us. Usually we are interested in the results. Good. Everything clear so far? Because now we go really the parallel steps. Okay, you see some nodding in the back. You're still in the course material, I hope so. Good. Because this is essentially, then when you understood this part, then you're more, in the parallel world, and then we can really get going to larger applications. Because Hello World is quite boring, I know, but it captures still the essence that you have. In order to do so, no basically surprise, we would have a job script, and we take our C job script that we have, we just add a couple of things differently. And this is, we take a new name. Okay, that's maybe good for us to help us in the schedule to understand this. But we see here, we remain in one node and will execute basically this task on this node 4 times. Hence, it's now the major change. Before Hello World, I had 1. And then the scheduler knows, okay, I just use 1 task in 1 node. Hence 1 core, done. Now we have 4. That means we come basically to the realization of what you just see here now. With 4 cores. Nothing prevents me from doing now 8, right? Maybe 15, and I will demonstrate this a little bit. Then once, when you take a certain number of tasks per node, you will also have the limit of 1 node, right? You cannot have infinite there. So you have to specify maybe 2 or 3 nodes. But this is something what I will rather show in practice on Monday morning in a pre-recording, by the way. So again, I will be not standing here, but still, let's see fundamental difference. And this is now the interesting scalability part. When I put here 8, everything will be prepared to just basically do this 8 times and not 4 times. And the output would be the same. I'm 3 out of 8, I'm 5 out of 8, and so on. And I never have to recompile the C program. So that's obvious. Important also, as you remember, we have an MPI implementation now. So we have to load this module also for the environment. Why? Because I basically have used the login node, right? I was not using the scheduler yet. I was on the login node. I was doing my module load as here, then MPI compiling it. That means the processor on the login node knows that I need MPI and use it, but the compute nodes, which you have here, don't. Hence, you have to basically also inform with the job script what environment, what module should be loaded on all the different processes that are involved, so that you have, again, MPI available. Otherwise, of course, Hello World will crash because we use MPI statements. Good. And this is a stepwise workthrough that almost, in a one way or another, is the same recipe for MPI programs, right? What you just have seen, all of these steps, SSH, compiling C, then adding MPI statements, adding modules, and so on, and then the job script. That's essentially what you have in parallel programming, and essentially what you can take as a modus operandi along the way. So let's go a little bit further. Yeah, this just summarizes, of course, the whole process. Again, earlier login node. Important is that we were there, we compiled there. So the earlier login node knows that we want to use MPI. But the processes here on the compute nodes don't. Hence, I put the module load OpenMPI in edit so that we can actually execute the MPI hello beautifully. When I do this, I get a nice job ID back. If you know from the practicals, that is a very important part for you. It's, again, unique. It has nothing to do with a unique rank. This is a job ID, your task that you have here, so that you can always see the outputs. You can see if it's still stuck in the schedule. In the assignments, it will be basically sometimes possible that when you do it at the same time, you face the limits of our teaching partition Newton, because there are only 4 nodes, compute 0 to basically the first 4. And then basically there are not enough cores maybe available. So you have to wait. And you would have something like SQ to check where's your job. Also, this I will demonstrate in the practical lecture. But this job ID is something that you then basically should remember when you do this, right? When you basically submit your job because you want to have the results. Here's one example. If you remember in the lecture before, I said you can specify with spatch output and error the exact name of the file. If you don't do this, there will be a default that you see here, slurm job ID. Now it's the same job ID you submitted in, output, right? So You can do it differently. You could put just output, but important in a way, if you have now several ones, you see I executed this twice, you will have different job IDs. And if you change the source code over time, of course, maybe it's smart in the output also to have the job ID inside. And you can play with this a bit. SBatch enables you to have some variations of it. And when you now go into the file, there's one interesting effect. Again, the ranking order here, right? This is now very beautiful. You see 0, 1 of 4. I am 1 out of 4 and 2 and 3. There's no 4 because the rank start is 0 to 3, although we have 4 processes. But you will realize when you execute this a couple of times that the order might change. You would have sometimes that 3 is the first and that 2 is the first, whatever. And this is, again, the point that basically we don't have parallel I/O. This will come in later lectures, right? We have just parallel compute. That means every time a processor says, now it's time for my printf, I need to get access to the output file. And when you have access to the output file, it's basically blocked for the others. So they have to wait and then can write. So depending if there's a, let's say, very tiny time step where this 0 process was lucky before the 1 to be ready, it just got the file and so the others have to wait. But could be also that the process 3 is ready to execute. Good, and I think that really summarizes the very trivial task of doing hello world 4 times on these nodes. We basically realize it's almost similar like we done before, right? C programming, we just add MPI statements, which is now, of course, our parallel programming. This is where you spend your time. This is just the normal modus operandi. You will compile, SBatch it, compile, SBatch it, status, output. There's something wrong, SBatch it. But the real time you spend is on the application logic with MPI, the parallel program. So let's move into that a little bit. Maybe here it's again important to think if there's any questions around this, what I presented, because then we go to the next steps now using rank information and things like that. Seems to be not the case in class. For the participants online, of course, you're part here. Just put something in the chat. It should be blinking. Then I realize that you have a question. Good, but let us come then, if there's no question, to a better understanding now how I can use this beautiful application logic in the environment and based on ranks, and then do things differently, although we have one source code. That is now the challenge, right? One source code, and we want to do different things with one source code. So that's something where we now go to, ending up with a ping and pong. So again, to understand what this environment is all about, it's important to understand that we have usually this include file. You have seen the MPI header, and that we have this sort of MPI environment part where you have some parallel code that you can really use. And here you can do a lot with message passing. You can do send and receive. You can do MPI broadcasts, scatter, gather, the things I had, let's say, conceptually in the first part. And they all will do basically and involve a different region. Important is to realize that your rank information or the size or so outside this environment is not existing, right? So it's really MPI init and MPI finalize, and in between you work. Now, how you work depends heavily on your application, but in a more zoom in, if you want, for instance, for the send and receive that we will now look a little bit into, we have again the idea of 2 processors that maybe should do a send and receive, and that you basically have both your memory space, you have basically some data in both of them. And let's say one process should be update the other process for a certain variable. That's often done in these time steps. That's why we do send receives. In order to do this over the network, we basically need to prepare a little bit space. We allocate space and memory to receive data, right? Yes, of course, for your own data variable is already some space reserved, but if you want basically for receiving it, you have to basically have an operation for it. Hence, a receive will prepare and allocate data for this variable that you send over the network with MPI send to MPI receive it. And then you can, if you want, basically modify your own memory space with the data and do what you want, right? We will have several applications more and more. But it shows a little bit how the system works with the system buffer that you need, because you send it over the wire, so to speak. It's a very short wire, InfiniBand, hopefully, from one processor to the other inside a HPC machine. So very low latency, very quick, but still, we have still different processor. It's different, basically that's why the network protocol of MPI needs to find this different processor and so on. And that's why this is also a very low level, fast protocol and not to be used over the internet, right? Because this would be unsecure. Good, but that was the next step to realize now, obviously, the identity of processor 1 and processor 2 we need to understand, we need to get out when we want to do this send and receive. I already showed you this conceptually, how it works. So essentially, again, if you abstract it from NTI point-to-point communications in general, you have your own memory space. Your processor will get it in the system buffer. You still have, because it's the same source code, right, your data in a different space and need to receive it in your own processor to maybe do something with it, maybe do an addition, whatever you want to do. Another part is that over the time, although all have the same, let's say, source code, the data in it could be very different. That's another part of this, right? Because you send receive, again, with different variables, you do lots of different elements. It can be that the data is always very different, although it's the same source code. Another way of thinking about these applications, right? When you have, let's say, these four that are here working in different manners. One could be the ship moving from this location to the other location, could be the wave height to another wave height in another part of our Cartesian grid. By doing so, you always involve two processors, very simple, of course, but that's why we start with an introduction to MPI here. Let us now think when we go one step ahead. Now it's getting a bit more interesting. And again, I will demonstrate this as practical lecture 2.1. So if you don't understand perhaps everything, that's all right. Firstly, think about that I have basically here a C program, as we just discussed with Hello World. So I will just compile it once and I'm done with it. Now we have two processors with the same source code, right? Now, how we in the world should now do a ping and a pong, right? So that's something now to think about. I want to do a ping on the one hand and then also a pong. And as we just learned, I cannot just do a ping without being ready to receive a ping. And after that, then I can do a pong back. Hence, not simple table tennis, a bit more elaborate because I have to prepare for things like that. The other aspect is what you already know. So here's basically the MPI init. We do the size and the rank. So sometimes it's called number of tasks and size. It doesn't matter, it's just a variable name. We have a little bit of news about the MPI status variable. That's for us helpful to understand what was going over the wire, what was basically transferred, some status that we can use. And when you now execute this, the interesting thing is, as you know, it is twice on processors. Essentially, we want to come to something that looks like this. We have two processors involved. I specified this with my job script, and one have rank 0 and one has rank 1. Right, this is what the MPI environment gives us. So in other words, when I now run this source code, one processor will come to this, right? It will say if rank 0, that's me, and will execute these parts of the application logic. But the other processor would say, well, I'm not rank 0, I am rank 1. Hence, we come now to this situation that we can say one is responsible for send, and the other one is responsible for receive. Right? In the other words, as I said, the handball player, they look each other in the eye and said, okay, you have the ball, you're the send, and I am the receive. Yeah, ready to receive. In order to be ready for receiving, you need certain buffer spaces. You want to understand how much basically I get, which is of course now dependent of how much you send. So you have to specify also, is this an MPI char you put over the wire? What is it, right? You could be having strings, could be different, integers and so on. So basically what you have is a send receive. You have to understand, of course, what you want to pass, what data you want to pass. Here in this example, it's one char that we want to do as a ping and pong, right? This is important. Another interesting element is, of course, in this particular view on these applications, you also have to understand that you basically need to understand that you have to specify, so to speak, the process that you want to address to, right? So you would have a destination and source, And basically the other one as well, where you want to basically understand, so when I send it to this particular destination, in other words, in MPI send, basically then I'm ready to get something to rank 1. Of course, this is different now for the receive, that is basically want to get something from the other kind of rank. So this is something where you have to have the matching numbers in this kind of variables, and to understand then the source and destination, right? Don't get this confused with the ones, that is just the length, so 1 MPI chair. But that's why basically the source says 0, because we want to have something from rank 0, and receiving it. And when I then basically have the MPI send, I want to have the destination 1, and then basically, destination 0, because I want to send something to rank 0. And the opposite, of course, is true. Basically, I want to send something to rank 1 as a destination, which is this fellow. And then I also should be receiving something from rank 1, which is send 1. This could be in a bigger application quite misleading. So if you have a larger application, obviously to get more and more to the problem, lots of variables, lots of sources and destinations. Hence, you would say from practice, this send and receive is just used here and there for individual configuration steps for individual elements. Rather, the broadcasts, the collective operations are much more used in practice, right? So hence, this is also very limited, because now I have a one-to-one application, right? I do my ping, which is here, to the first rank, and then basically I get something back to the 0 rank. This is also not really scalable. As we discussed, it should be independent from the submit operation, right? So when I now execute this 4 times with the submit script, we have still the same application logic. So what will happen? Anyone an idea? What happens if I have 4 processes? With the application logic here, think about that one will execute this. Yeah, please. Good. Yeah, one here in the course got the message, basically, essentially, very good. You would have assigned rank numbers for all 4. That means 0, 1, 2, 3. 1 is executing this part, rank 1 is executing that part, and rank 2 will be neither, right? So there's no ping pong, basically, essentially, a handball player standing in maybe as a goalkeeper somewhere else, not being involved. So hence, this would be then probably also rubbish, because as rightly put, we want to read out the status that comes back and is filled by these variables, which only are executed again in these operations by rank 0 and 1. Hence, this would be basically twice okay for rank 0 and rank 1, but not okay for 2 and 3, right? So for the other 2 ranks, which are not addressed here. And now when you scale that up to big applications, you will understand that programming in parallel is not that trivial anymore. If you have very specific extra roles that specific ranks have to do, you really have to get this into your mind, or also start with blueprinting, let's say, an architecture diagram of your application logic. So what should what processes doing? Here's then, of course, a little bit just to complete this example, that you also put out how many chars you really got. That should be, of course, 1, which you can get out of this basically status MPI tags and this kind of source information. So a little bit of output. Again, if not everything is perfectly obvious to you, I will do this on Monday and give you, let's say, a real tour on a demo. When you see it in practice, when we submit hello world, and then start from this, submit ping pong, and so on. Yeah, towards the end, let's get to a little bit more other part, because it's another, as I said, basically more important idea of how to use MPI. And these are the collective operations. I just provide you here with one example. Your goal in the assignment will be to use all of them, right? You will not program them. Basically, you will just execute them and see a little bit what the output is. So don't worry. As I said, it's not a C programming course, more or less. It's just really thinking about in parallel. I demonstrate you here briefly the broadcast. Also, this I will present, of course, on Monday. Remember what I had in the first part of the lecture. This is now the idea of addressing a lot of different cores at the same time without the need now of send receive. I could model this in a for loop, right? I could say send, receive, send, receive, send, receive, send, receive. Here, of course, I just want to have a send, not a receive, sorry. But in the end, you could do it in a way that you have lots of source code lines, which is programming badly parallel computing. We'll have also a case for it in lecture 3, where I show you these examples. Lots of loops to do always send and receives instead of doing one source code line with a broadcast, right? This might be 20 lines of codes or more when you do this with 4 and send receives and so on. Hence, it's a more smarter way. And I would say also from internal perspective, it's differently programmed after tree structure. So it's also much more efficient than just going with for loops. However, you know, it's based on a communicator. So we basically are very free in the number of processes we have here. Hence, this is also directly scalable, again, with a job script. No, this kind of rank 0, which we directly specify. The only thing you have to specify a little bit is, of course, so to speak, the root, right? Assuming again, and this is now the last example, then we break, think about everybody has the same source code, right? It's again an important part to think about that one has now a special role of being the source of this broadcast, right? Hence, we have to use our rank information to basically do something with it. Here we do some initialization and then do a broadcast, but everybody does a broadcast, right? Hence, we have also to specify who of all of these ranks is now the source. And here in this example, it's source 0. So basically rank 0 is doing this. And with this, basically then everybody should get this information in this kind of things we do for MPI inits over the wire. So this is basically what you get from all the others, but only the first rank 0 is actually filling the buffer. That's how you can check if you really got something sent, because now after the broadcast, everybody has to get out basically the idea of the buffer here, which is nothing else than, let's say, this 4 chars, 4 ins that we have basically put over the wire. I will demonstrate that also on Monday, and then it's getting a bit clearer now, I think, how you efficiently can do MPI programming. I think for today, we covered already a lot of material. So I think we are done here. There's, of course, this video that I would recommend still you to look. I will play it now, basically, but you don't have to be staying here. Maybe go already to the next class. But still, it captures the essence that we all learned, and I think in a very nice graphical fashion, right? It's not from me. I think it's still MPI for Pi that is also there introduced, but it has a very nice illustration, again, from all these different methods, gather and so on. There's also some additions to it, which I found good. This is all gather, so that basically not only one processor is gathering the results maybe, but all the others as well. It's also incredibly often used. Hence, I think with this, I'm done for today, unless there are any questions.